Lecture 10-2, Calculations Involving Gases and Gas Stoichiometry. Density calculation. What is the density of a 500-gram sample of chlorine gas, Cl2, at STP? Recall that STP is standard temperature, 0 degrees Celsius, and pressure, 1 atmosphere. Under those conditions, the molar volume of a gas is 22.414 liters per mole. Thus, the mass of the sample must be converted to moles, and by use of the molar volume, the volume can then be calculated. The moles of chlorine gas are 0.500 grams divided by 70.90 grams per mole of chlorine, which is equal to 0.00705 moles of chlorine gas. Multiply this by the molar volume at STP, 22.414 liters per mole, and the volume is 0.158 liters. To get the density, take the mass and divide by the volume. This is 0.500 grams chlorine divided by 0.158 liters, which is 3.16 grams per liter. Density and molar mass. The molar mass of a gas can be determined by knowing the density, temperature, and pressure of a gas. The derivation is shown at the top. Substituting nRT divided by P for volume in the density equation, mass divided by volume, we get mass times pressure divided by moles and R and temperature. Rearrangement gives mass divided by moles times pressure divided by R and temperature. Since mass divided by moles is simply the molar mass, we find that density equals the molar mass times pressure divided by R and temperature. A further rearrangement shows that the molar mass of a gas M equals density times R times temperature divided by pressure, or the molar mass of the gas equals mass times R times temperature divided by pressure and volume. To remind you, pressure must be in atmospheres, temperature must be in Kelvin, volume must be in liters when using R equals 0.08205 liter atmospheres per mole Kelvin. Molar mass calculation. A 2.10 liter vessel contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass of the gas? Use the molar mass of the gas equals mass times R times temperature divided by pressure and volume. MRT divided by PV. Thus, the molar mass is 4.65 grams times 0.082056 liter atmospheres per mole Kelvin times 300.15 Kelvin divided by 1 atmosphere and 2.10 liters. The answer is 54.5 grams per mole. Note that liters cancel, atmospheres cancel, Kelvin cancels, leaving grams per mole as the units. Gas stoichiometry. What is the volume of carbon dioxide produced at 37 degrees Celsius and 1 atmosphere when 5.6 grams of glucose, C6H12O6, are used up in the following reaction? Glucose, C6H12O6, plus 6 oxygens, O2, yield 6 carbon dioxide, CO2, and 6 waters, H2O. The strategy is to convert the mass of the glucose to moles of glucose using the molar mass of the glucose, then to convert moles of glucose to moles of carbon dioxide, using the molar ratio from the balanced chemical reaction above. The moles of carbon dioxide will be used in the ideal gas equation, PV equals nRT, to calculate the volume of the gas produced. The molar mass of glucose is 180.16 grams per mole. The temperature in Kelvin is 37 plus 273, which is 310 Kelvin. The pressure does not need to be converted as it is already in atmospheres. First, the moles of glucose equals 5.60 grams of glucose divided by 180.16 grams per mole, giving 0.03108 moles of glucose. Second, moles of carbon dioxide is 0.03108 moles glucose times 6 moles of carbon per mole of glucose, giving 0.1865 moles carbon dioxide. Rearrangement of the ideal gas equation yields volume equals moles times R times temperature divided by pressure. Thus, the volume equals 0.1865 moles of carbon dioxide times 0.08205 liter atmospheres per mole Kelvin times 310 Kelvin divided by 1 atmosphere. This equals 4.74 liters. Note that atmospheres, moles, and Kelvin cancel, leaving liters as the unit. Dalton's law of partial pressures. When volume and temperature are held constant, the total pressure, P sub total, of a mixture of gases can be considered as the sum of the pressures of the individual gases. Thus, P sub total equals the sum of the individual pressures, which equals pressure 1 plus pressure 2, etc. In the example below, a red gas is mixed with a green gas such that the total pressure, P sub total, equals P1, red gas, plus P2, green gas. Consider the previous case in which two gases are in the same container of constant volume and temperature. Thus, P subtotal equals N subtotal times R times temperature divided by volume, which comes from the ideal gas law. However, N subtotal equals N1 plus N2, making the total pressure equal to the sum of N1 plus N2 times R times temperature divided by volume. Separating these into individual terms, the total pressure equals N1 times R times temperature divided by volume plus N2 times R times temperature divided by volume. This, in turn, equals P1 plus P2. Generically, the pressure of an individual gas in a gaseous mixture equals the number of moles of that gas times R times temperature divided by volume. Next, we define the mole fraction, X sub I, as the number of moles of gas I, N sub I, divided by the total number of moles of gas N sub total. With the mole fraction known, we find the partial pressure of an individual gas, P sub I, is the mole fraction of the gas, X sub I, times total pressure. Calculation with mole fraction. A sample of gas contains 8.24 moles of methane, CH4, 4.21 moles of ethane, C2H6, and 1.16 moles of propane, C3H8. If the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of propane, C3H8? The mole fraction of propane, X sub propane, equals the moles of propane divided by the total moles of gas. The total number of moles equals the moles of methane plus the moles of ethane plus the moles of propane, which equals 8.24 plus 4.21 plus 1.16, giving 13.61 moles total. The mole fraction of propane is then 1.16 divided by 13.61, which equals 0.0852. The partial pressure of propane, P sub propane, is 0.0852 times 1.37 atmospheres, which is equal to 0.117 atmospheres. Using partial pressures. Heating potassium chlorate causes it to decompose into potassium chloride solid and oxygen gas. When the oxygen gas is collected through water, the gas becomes saturated with water vapor, producing a gaseous mixture. The amount of oxygen can be determined using partial pressures. That is, P sub total equals P sub oxygen plus P sub water. The total atmospheric pressure can be measured directly, and the partial pressure of the water can be determined from a table of water vapor pressures, which is dependent upon the temperature of the water. Gas diffusion and effusion. Gas diffusion is the gradual mixing of molecules of one gas with the molecules of another gas by virtue of their kinetic properties. The upper right picture shows the reaction of ammonia gas and hydrogen chloride gas to make ammonium chloride, which is the cloudy appearance over the bottle of hydrochloric acid. Not only does this picture show that the ammonia and the hydrogen chloride diffuse through the air, but it also demonstrates Graham's law. Graham's law states that the rate of diffusion, or effusion, is inversely proportional to the square root of the molar mass. This basically means that the larger the mass of the gas, the slower it moves. In the reaction of ammonia and hydrogen chloride, the hydrogen chloride moves slower because it has a greater mass, 36.46 grams per mole, than the ammonia, 17.04 grams per mole. Thus, the cloud of ammonia chloride appears mostly around the source of the hydrogen chloride, which is the hydrochloric acid. Gas effusion is the escape of molecules from a container into a region of vacuum. The picture to the lower right shows gas escaping from the left side through a hole into the vacuum on the right side. Deviations from ideal behavior. For 1 mole of an ideal gas, the calculation for the number of moles from the ideal gas law should be 1. That is, N equals pressure times volume divided by R and temperature, which equals 1. There are attractive and repulsive forces at work in real gases. Repulsive forces become especially present at high pressures because the volume between the gas molecules gets smaller. Also, as a result, the actual volume of the gaseous molecules affects gas behavior. Furthermore, attractive forces are present in polar gas molecules. As these molecules get closer together due to higher pressures, they interact more. Also, as polar molecules slow down due to lower temperatures, they interact more. As such, lower pressures and higher temperatures provide conditions that are more likely to be ideal. Van der Waals equation for non-ideal gases. The equation is pressure plus a times moles squared divided by volume squared times volume minus moles times B equals moles times R times temperature. The terms A and B are called Van der Waals constants, and they are determined experimentally for each gas. The first term in parentheses is the corrected pressure. It represents the number of intermolecular interactions, which is proportional to the square of the number of molecules per unit volume. Moles squared divided by volume squared. The second term in parentheses is the corrected volume. It represents the small but not truly zero volume of a gas. Thus, it is proportional to the number of moles.